solving rational equations. Now that we've reviewed how to add, subtract, multiply, and divide rational expressions, we're putting into some applications here. This problem is a very typical kind of problem. I want you to pay close attention to how they ask the questions. So here we go. Arthur and Shanine can paint a wall in 6 hours when working together. Shanine works twice as fast as Arthur. How long would it take Shanine to paint the wall if she were working alone? So this picture actually really helps us to see that there are two of them together. They finish it in 6 hours, excuse me. Which means if you want to write it out, each hour they finish 1/6 of the wall. Finish painting 1/6 of the wall, right? So Shanine works twice as fast as Arthur. So let's look at Arthur first because Arthur is the reference point. Let's say if Arthur by himself would spend X hours to paint the whole wall, right? And then Shanine's time, how do you spell Shay? Would be 2x. It will be, I'm sorry, it will be not 2x. Shanine is twice as fast. So be very careful here. I almost made that mistake. So Shanine only spends x over 2 hours to paint the wall. So those are the information that's been given. And now it's asking you, how long will it take Shanine to paint the wall if she were by herself? So what we do know is that here, if Arthur to paint it, Arthur would be painting 1 over x of the wall per hour. We know that, right? We know together they will do 1/6. Then we also know, we're going to flip that, it's 2 over x of the total wall per hour can be painted by Shanine. So there exists an equation where 1 over x plus 2 over x should equal 1 over 6. And if you do your math right, this is pretty easy, x should be equal 18. So if x is 18, then you can say Shanine will take half as long, so it's 9 hours to finish painting the wall. Okay? So that's the thought process. Again, let's go back to do a quick recap here. What I want you to pay attention is this is one of the things to figure out. As soon as they give you 6 hours to finish something in total, you know, especially if the total is not given, you can use 1 as an abstract total. And then each hour together they finish 1/6. Then the next thing I want you to pay attention is once you set the reference point, be careful. Do not make a mistake here. I'm going to use a different color. Maybe I'll use this gold color here. This is what this common error was referring to. I almost made that mistake, right? So always go back and double check and say Shanine is faster. So obviously 2 over x is faster, is more than 1 over x. If you did 1 over 2x, you know, it probably can split. I can see myself easily make that mistake. But then, you know, 2x is greater than x, so that total number is less. So how can a Shanine paint less in an hour? It doesn't make common sense. Okay? What's the solution to this equation? Now on the left hand side I've got an addition, on the right hand side I've got a rational function. So probably I need to use proportions, right? And before I do that, I'm gonna finish the addition on the left hand side. So if I multiply x minus 3 to the first term, I would multiply, and I'll put it in parentheses, x minus 5 to the second term. On the right-hand side, I can factor this fairly easily. It should be pretty obvious. It's x minus 3 times x minus 5. You know, otherwise you do the factoring process on the side by hand, right? Negative 3 times negative 5 give me positive 5. And I would have negative 8. All right, so right now on the side, pay attention. At least I know for this equation, x cannot equal to 3, neither can x equal to 5. All right, let's continue with this. It looks like the denominators are exactly the same. So I'm left with x minus 3 plus x times x minus 5 equals 2. If I want to do some distribution, I would end up with this. And then I reorder it and combine like terms. Looks like, nope, that's a 5. No, that's a 4. Negative 4x. Is it? Yep, negative 4x and minus 5. Okay? From here, it should be a pretty straightforward factoring quadratic times x plus 1 equals 0. So my calculation yields two results as expected. I have x equals 5 and x equals negative 1. Now, since we know previously right here on top, I said x cannot equal to 5, nor can x be 3. So this one has to be carved out. So we have to cancel that one. So your final answer is x equals negative 1. So if you throw this function into the one on the left-hand side and the one on the right-hand side into decimal, this is what you'll be seeing. Let me see if I can make this bigger. Okay, here we go. Okay, it's covering some of my calculations, but that's all right. As you can see, the blue one is the one on the right-hand side. Okay, and then there are two asymptotes that neither equation approaches, and this asymptote is x equals 5, and this is x equals 3. So that's how we know the function does not touch x equals 3, neither does it touch x equals 5. Excuse me, so that's why that 5 has to be out. Now, in order for these two functions to equal, they have to meet at this point, which is negative 1. That's our answer, our solution. And at that point, we know the y value is 0.063. So you verified it with your graphing calculator that this is correct as well. Okay? Okay, what are the solutions to the following equation? Notice here it says that we're trying to solve problems with extraneous solutions. So there are mistakes in your final conclusions, and you have to find a way to double check it. Okay, now in this case, we're asked to solve this. What's the domain for this problem? Obviously, x cannot equal to 2. So let's begin solving it. There are, again, different ways to solve it. You can find the common denominator on both sides and then pay attention to the numerator like we did in the first problem. But this time, I'm going to multiply the denominator on both sides, which is another way of solving it. And that way, this gets canceled. So I have 5x left on the right-hand side. And then I distribute, and so that these two gets canceled as well when I distribute it over to the second term. So I would have plus 10. So, okay, now, does not look like anything more than algebra 1, right? So now, guess what? I have negative 2 over negative 4 over negative 2. And my final answer is x equals 2. What did I say just now? I said the domain here, x cannot equal to 2. Or you can substitute, you can use substitution and then bring this entire term into your x's. And then you'll quickly find out that this does not exist, right? This equation does not exist. So the final answer is does not exist. There's no value for y. There's no value for x that will make this equation happy, that can balance the left-hand side with the right-hand side. That's what it means. Before we begin this problem, I want to do a quick review of some pre-algebra problems. Here's an example. Let's say I have to bike from Princeton to New York City and then come back, okay? Then come back. So on the way there, if I don't have any wind, my average speed is 30 miles. And let's say the total distance in between is about 50 miles in total. That's the distance. So 50 over 30 miles per hour would give me the actual hours of how many hours needed on the road by bike, right? When I bike from Princeton to New York City. That's when there is a beautiful weather, there's no wind, there's no headwind, there's no tailwind. So that's scenario number 1. Scenario number 2, now I have headwind, so it's blowing from into my head, it's stopping me to go as faster. So in this case, my average speed has to go from my original speed, and the headwind is 8 miles. So now my new speed is 22 miles per hour. So I'm going slower, right? If I go slower, the distance hasn't changed, but the denominator is smaller. So the total amount of hours has been increased number of hours needed on the road. This makes sense, right? Third scenario, if I do a third example, is a tailwind. In this case, let's say the weekend after, I've got tailwind of 6 miles, so I'm traveling 6 miles faster per hour compared to previously, miles per hour. And distance is still 50 miles, and now it's 36, and obviously I need less hours, less time needed on the road. Okay, so this is a pretty simple example, and I can ask the same questions in a slightly more abstract way, which is what we got here in example number 5. Let's read it first. Paddling with the current in the river, Jake traveled 16 miles. Even though he paddled upstream for an hour longer than the amount of time he paddled downstream, Jake could only travel 6 miles against the current. So right here we've got quite some information, and then in the end it tells you that his average rate, let's just call it paddles at the rate is 5 miles per hour. This is important. And then it's asking the speed of the current. So obviously upstream it would be 5 plus c, downstream would be 5 minus c. Okay? And so when he goes against the stream, upstream, he only travels 6 miles. If I have 6 miles here and I know the rate is 5 minus c, I have the total amount of time, right? So I can note this is number of hours traveled upstream. And then it says traveled upstream is an hour longer. So whatever, in other words, if I go for the downstream here. If I do downstream, I travel 16 miles in total, divided by 5 plus c. And then if I add an hour, these two would equal. So my final equation here becomes like this. And you need to solve that. All right, I'm not going to go into the details. You all know how to solve it. Your final answer is c equals negative 25 and c equals 3. Obviously, the c equals negative 25 can't be because time cannot be negative. So this is an extraneous solution. Your final answer is the speed of the current is 3 miles per hour. Okay, the most important thing here is this setup right here. Understand what the problem is talking about and go from there. Here's a summary of rational equations and solve them. Basically, what you're doing is that you're looking for LCMs and try to find ways to get rid of the denominators as much as you can. However, in that process, whenever you get rid of a denominator that involves a variable, you want to reevaluate your domain because that will eliminate some of the possible solutions in the end. Okay, we also covered how to solve equations with extraneous solutions. So you can either plug it back in or you can interpret it if it's an application problem. All right, guys, I'll see you soon.